So why is it so terrible? Why does this feel so terrible?
Okay, as said, as Sue requested, Sue does not need any introduction. But Coppersmith, University of New South Wales.
There you go. See, isn't anything? Oh, it's like, oh, but then this is weird, but that's better.
Yeah,
Yeah, that's much better because I was putting it over. Oh, and I can do that. No, I can't do that.
Something has a clip.
No, no. Oh, I see what you're saying. No, I didn't see a clip. If I saw a clip, but that's okay. All right. Okay. That's as good as it's gonna be, I think. Yeah, so I'm gonna talk about so the work I've been doing on quantum computing, and I've been my work on quantum computing started a long time ago, actually, like 20 years ago. But I've continued it since coming to Sydney remotely during the pandemic. It was like actually surprisingly little change because we just were on Zoom anyway, and it made no difference. But actually, the last couple of years, we've made sort of progress that might that we think might be really important for scale up. And so that's what I wanted to talk about. That is not, oh, this is, no, it should work. All right. Well, it worked before. Well, no, we're back to that thing where it froze. It doesn't work on the. We've had a few technical glitches.
I had to click on that screen.
Okay, so that's, yeah, and it's like once it works there, it works there. Okay. Right, so now watch this, the eclipse. Okay, and so these are my collaborators. The main collaborators on this are Mark Friesen, who I've been working with for a really long time, is a research scientist in Madison, and the student who's done the most directly relevant work is Merritt Loser, who will be graduating soon. And then Ekmel Erkan did some work that I'm not sure I'll show, but really relevant on interaction effects in these quantum dots. And I will show a little bit of his. And then Bob Joint, who is he just went emeritus, but he was at Wisconsin a long time. And then you may know Rajiv Raban, who's at UNSW, he's down the hall. And then Giordano's Capucci is at TU Delft. Mark Erickson sort of started this whole thing in silicon-germanium in Madison. And then Brian is the grad student who did the experiments that sort of led to all the work we did. And Tom McJunkin did some other experiments that I'll tell you about that were, it turned out everything folded together into a long paper with many authors. Okay. So I think I'm the only person in Australia who works on silicon-germanium, so I have to tell you about silicon-germanium. There's a big effort in Australia. Several groups work on silicon quantum dots, but they work on silicon without any germanium in it. And it turns out that silicon-germanium is also a well-known manufactured semiconducting material. And in fact, what I'm going to show you later is that Intel is has gotten into the quantum computing business, and this is the platform that they're using. And so our work we have a non-disclosure agreement with Intel, so I can't tell you, or I'd have to kill you kind of thing. But I'll tell you, I do have some Intel data from later, which was publicly released. But anyway, the principle is the same. Okay, so morally speaking, in terms of manufacturability, it's like silicon in the sense that it can be made in fabs, and Intel is actually selling chips, 8 qubits that don't do a hell of a lot, but nonetheless, they're selling chips, computing chips. Okay, so that's the thing. So it's like silicon, but different. Okay, so I have to tell you why it's like silicon, but different. Okay, so the overall thing, everything I'm going to tell you, except for this thing, this is the quantum well where the electrons live, and you can see it's like down a bit, and that's what silicon-germanium does for you. It moves the electrons away from the oxide. So here you have metal gates, and then below the metal gates there's an oxide, and to first order, all the terrible things that can happen to screw up the coherence happen in the oxide. Okay, and so basically you can move the electrons down and it makes the oxide go farther away, and that's why it's potentially better. Okay, so everything else is the same as silicon, just regular silicon. Okay, here we are. I don't know what that was. Okay, so I don't know if it sounds, it still does something though. Okay, I'm not, and I'm still alive. It didn't electrocute me. Okay, so anyway, so what happens is you apply voltages to these gates, and then, you know, if this is a usual 2-dig situation, you apply voltages to the gates, and then you can sort of deplete the 2-dig, except where you have quantum dots. And the thing which is nice about it is, this is not, by the way, you know, this is an artist's rendition. This is not a real device. But the thing that's nice about it is that the qubit is in a place that you decide. So the same gates that you use to define the qubit are the gates that you use to manipulate the qubit. So you don't have an alignment problem, which you can have if you're doing implanted donors, which is you know, another popular approach. And then you measure things using a spin to charge conversion, and that's all done the same way by everybody. Okay, so so first there's the question of why do silicon, and silicon is popular because it is known that you're going to need a lot of qubits, and if you want to have a lot of qubits that all work, it's nice to be able to leverage all of the billions or maybe even trillions of dollars that's gone into scaling of classical electronics. And so I'm not promising anything, so that's why it says plausible paths, okay, to scalability, but there is a lot known about how to scale classical electronics, and some of which is, you know, quite relevant to quantum electronics. The thing is, of course, it's more, I mean, quantum computing is more finicky. Okay, so it's not like you just do it, you know, you can't just adopt it wholesale, but certainly a lot is known. And then the other thing, which I think is, you know, really very clear cut you can do, is you can put classical electronics and the qubits on the same chip because they're made exactly the same way. And there's been, you know, a lot of work on that, on just sort of integrating everything. And since it's the same substrate and you're doing something that has already been used for classical electronics, it's pretty clear that you can the integration. So this plausible is like a lot less plausible than that plausible. This plausible, I should probably say, clear cut. Okay. Anyway, and so then the picture of this is just to say, oh, look, it's really not so different. This is actually a picture from some NRC report from 1988. This is super fancy because of that low view. To do that in an electron microscope is actually, you know, really very high grade. And so, you know, this picture has been reproduced more times than you would think possible, just because it's so classy. And so this is from, again, 1988, and, you know, this is these are the gates, and it's quite amazing how great they are. But anyway, but this is a picture of like our very first quantum dot qubit that worked. This is the device, and it's made the same way. These gates are, you know, not a classy electron micrograph, but, you know, you can see the scale's a little smaller, but, you know, it's same order of magnitude. Okay, so it really is like classical electronics. And that, I should probably change this, because again, now that Intel is making these chips, you know, you don't need to imagine that this is true. It's like they run them on the same fab lines that they run other things. Okay, so I did want to just talk a little bit about why silicon-germanium instead of silicon MOS. specifically silicon MOS. I work with the silicon MOS people, so I don't want to trash silicon MOS. Silicon MOS is what Dirac is doing, silicon MOS quantum dots. And again, so they've made qubits and they've shown high temperature operation. They're doing great work, but this is the advantage of silicon germanium, is that in silicon MOS, this is, here M is metal, okay, and metal oxide semiconductor. And in silicon MOS, the electron, and you're applying a big voltage to these gates to pull the electrons up to form the qubits. And so the electrons live really close to the silicon dioxide interface, and that tends to be quite defective. And there's a lot of evidence that in terms of charge noise, most of the charge noise is emanating from defects in the oxide. All right. And this just shows, this is just figures of how they work, and basically you apply the voltage, and then that's what draws the electrons up. So this is the conduction band, and that's the electron in the dot that forms the qubit. Okay, here's silicon germanium, and again, everything is the same more or less, except that the oxide layer does tend to be thinner, but that's sort of irrelevant. But there's this thing that's usually called the spacer, which is silicon germanium, and the electrons live in this silicon quantum well. So it's like silicon germanium, silicon germanium. It's like a sandwich. It is a sandwich. And the electrons live at this interface, and this is a very nice epitaxial interface. This is the band offset between silicon germanium and silicon, and that's what keeps the electrons living at that interface instead of at the top interface. Now you can definitely apply really big voltage and pull the electrons up. It's called, up to the surface, but you don't do that, right? But the whole point is to be to have the electrons living at a really nice interface. And one of the things that people have looked at quite a lot is how thick do you want to make it? It turns out that the control is better if you have this thin, but then you're closer to the defects. So there's a trade-off in terms of the depth. And so typical depths are 30, 40 nanometers deep. Okay, but still that's pretty far on the scale of getting away from trouble. Okay, so this is actually, I would say, the most successful semiconducting technology that's been demonstrated to date, just by the number of qubits. Okay, so silicon MOS, they at the moment they've only, again, and it's a yield problem, and the yield is because of these defects, and bad things happen by the defects. I will say that the Dirac people are basically going to semiconductor foundries, and so they're hoping that by, again, using real industrial processes, that will improve the quality of their qubits. So they do have a plausible scale-up path, but at this point, this is the most qubits. What I'm showing you is the most qubits in this architecture, in this class of materials. Working qubits, doing 2-qubit operations between every pair with reasonably high fidelity. Here, they're not super duper. This is a 6-qubit device, and the fidelities are a couple or 95. But again, one of the problems here is that we're looking to scale, and so everything should be 99% plus. Okay, so but this is state of the art for semiconducting. I should say in germanium, it's comparable. So there's germanium, and there's germanium in the same kind of heterostructure structure. It's comparable to silicon germanium, but between silicon and silicon MOS, silicon germanium and silicon MOS, silicon germanium is much further advanced in terms of size. Now, this is, if it had worked, a really, really interesting experiment. So I wanted to highlight it. It is 16 qubits. And the thing that's interesting about it is it has less than 16 control lines. And it's sort of, in classical electronics, the number of control lines that you use to control an array, it goes like the square root of the number of bits. That's called Rent's rule. And that's much harder to do quantum mechanically, using it for to make qubits, just because there's so much more fiddly. But they were able to get single occupancy of dots, so potentially qubits with basically Rent's rule type topology of the gates. However, in this paper, they don't show any qubits. And so we suspect what happened was when they tried to control the qubits, like they just weren't able to, there was just too much crosstalk. So that is something that, their 16 qubits looks pretty good, but the fact that it didn't work in terms of quantum control means that, there's more to do. So I'm just trying to be a little honest about what the current status is. Okay. But again, as far as I know, nobody's done this. This would have been by far the largest semiconducting qubit array. All right. Okay. But the fact that, I showed you like a lot of qubits and, and they all worked, is sort of evidence that sort of this idea of moving the electrons away from the oxide does improve yield and reproducibility. But what's happened is, as things have gone well, then you realize limitations that you were not focused on before. And it turns out that at this point, a big issue is what's called the valley splitting. I will define what I mean by valley splitting on the next slide. But basically, it's an energy splitting that you'll see in a minute. And it needs to be big enough, okay? And 100 microvolts, 0.1 millivolts is sort of the usual rule of thumb of what you want for high fidelity qubits. And what happens is that when people did this, just started doing it, nobody focused on the valley splitting that much. And it turns out that if you fiddle around, which is what you do when you're doing research work, as you know, you fiddle around, you can basically, fiddle around and you can find a regime where the valley splitting is big enough that you don't have to worry about it. And certainly, like in the experiments that I've been involved with, basically you might find a point in your parameter space where the valley splitting isn't big enough, but you just sort of change some voltages and move the dots around, and then, it's okay, and then you can proceed. So at the research level, this is fine, but if you're going to be making 1 billion qubits, which is really the selling point of these silicon kind of things, it's true, like, you saw, we didn't even, 16 isn't really working, but the goal is, like, if you get not very many working, you can scale it up to, literally hundreds of millions or billions. It's not, you don't want to be fiddling around. It's just not viable. Okay. And so we wanted to learn more about, like, what actually is determining the valley splitting. And, and what we really want to do is to, figure out how to get the big enough valley splitting with, this many nines, because again, you want, billions of qubits, and wouldn't it be great if you never had to worry about valley splitting again? And so that's the goal. Okay. So, the short story of the talk was that up until really pretty recently, like a couple of years ago, and I hesitate to tell you that I worked on valley splitting off and on since 2004, so it's actually sort of embarrassing that up until 2 years ago, up until then, we thought that the valley splitting came from the sharp interface. And at this point, I think it's indisputable that it does not. And actually, it is due to alloy disorder where the wave function lives. So either in the barrier between the silicon-germanium and germanium, or in the quantum well. Okay. And so basically, when you're futzing around trying to prove the valley splitting, if what you think is the cause of the valley splitting is not what it is, it turns out it's harder to control. So and I'll show you at the end, there's some quite a bit of it at this point, experimental evidence that alloy disorder does play a critical role, and figuring out how to exploit that to get to really high yields is non-trivial, but starting from the right, physics is helpful. Okay, so now I'll finally tell you what valley splitting is. Okay, so what's the valley? The valley is, okay, I mean, oh, yeah, sorry, guys. This is a silicon band structure, and the valley is the minimum of the conduction band of silicon. And again, you guys are all too young, except for Michael, to have seen silicon band structures in detail. But there's these valence bands, and they're if you're using holes, you're interested in what's happening in the valence band, and so and you see this degeneracy is a source of great excitement in the holes. But then it's a semiconductor, so there's a band gap where there are no states. And here's the conduction band. And in the lowest conduction band, you see, oh, gamma is sort of the center of the beryllium. That's K equals 0. Okay, and K equals 0 in the conduction band is actually a maximum, all right? And the minimum is here, okay? And that's the valley. The valley is the minimum in the dispersion in the conduction band, okay? And so you can look at this piece here and that piece there, and you get, here's the minimum, and that's the valley. And it's very reasonably close to the Brillouin zone boundary. Okay, so it's almost at pi over A. Okay, and so what happens is that because silicon has, I have to do the slide. Silicon has cubic symmetry, okay? And so if there's a valley in the x direction at 0.85 pi over A, well, then there's one here, one here, one here. There's 6 degenerate values because of the cubic symmetry of silicon. All right, so and that's true in bulk, but it turns out that quite a lot of the degeneracy is listed because when you have a silicon-germanium heterostructure, silicon-germanium is bigger than silicon because germanium is bigger than silicon, and it stretches the silicon well, okay? And so that big tensile strain breaks this degeneracy, so the out of plane direction is an equivalent from the in plane directions, and it happens that the energies in plane go up, okay, by quite a lot. So you never have to worry about these X and Y valleys ever again, like hundreds of millivolts, they go up, okay? And again, all these experiments are done below 1 Kelvin, so, anything above a millivolt you can ignore, okay? So then you have these 2 degenerate valleys, okay? And again, in the absence of anything else, they're degenerate. And that the splitting between those 2 valleys is what is called the valley splitting here. And again, what people thought was just the boundary here plus plus an electric field, either or both things lead to the splitting. Okay, and if you're doing single electron qubits, which is what all these figures I stole from Will Laurie's thesis, and he was doing single electron qubits, and basically he said, well, look, as long as the Zeeman, he was doing single electron qubits where this is the Zeeman splitting, as long as that is smaller than the valley splitting, and you never get excited if you never get excited into the other valley, it's all fine. And so what you need is for the valley splitting to be bigger than the Zeeman splitting. Okay, and it turns out that 100 microvolts is a good rule of thumb. And and I should say that the qubits I showed you were single electron qubits, so that's why this was an appropriate thing to show you. Okay, so basically now I'm going to get into like more detail about why the valley splitting is non-zero in the perfect heterostructure, and that okay. So and basically what happens is, you remember, it's like you're adding up states near the minimum of the conduction band, and so they have an envelope which is sort of normal looking bound state, but then there are these quite fast oscillations, okay? And there are 2 of them, right? Because you're sort of e to the I kx and e to the minus I kx, and so you sort of have twice as many states as you thought you did, right? If you do the normal thing, it's near k equals 0 and you have only 1 state in an envelope. But when you have the valley degeneracy, you get 2 different states with the same envelope, basically. Well, actually, exactly within this effective mass approximation, but different phases. Okay, and then you look at this and you say, oh, look, there's, you know, this is like a finite well. And so there's like this, you know, a little bit more of one wave function than the other in where the silicon germanium is, which means the energy of one state is higher than the energy of the other state. Okay. And if you have a perfectly flat and sharp interface, then you basically get a very large valley splitting on the scale of what is measured of several hundred microvolts. Okay. And if this is what was going on, everything would be groovy. Okay. And again, what we thought was going on for many years was like, and you do sometimes see really large valley splittings. And we said, oh, okay, well, why don't you always see it? And we thought it was due to steps in the interface. And and this is just to say, well, okay, you take this and the wave function is pretty rigid laterally. And so like one value will be lower here and another value will be lower there. And so then it just cancels, sort of a square root of n kind of situation. And so we said the trick, and again, we did this for years to people, the trick is to like get rid of the steps in the interface. Okay, and so then it became, and again, this turns out to be quite challenging on the growth side, because it turns out that actually the original interfaces where qubits were made actually were done with a on purpose miscut, because it makes the growth more regular, and then say, oh no, don't do that, we need it really flat, and that makes the growth more difficult. And so that had been the focus, to try to get like really uniform valley splittings for years. And basically it wasn't working. And that's why, you know, we could still earn a living this way. Okay. The other thing I want to say is it is actually really, really important to have big enough valley splitting. This is from a couple years ago now, but this is the Princeton group's qubit. Okay. And again, if you were a quantum computing pro, you're just looking at like, oh, wow, but I mean, you say the same thing as we would say, oh, those look really nice and it's all white and dark and there's no shit there. That's a technical term, but never mind that, it looks good. But here are the fidelities, and, you know, 99.95, you know, everything is over 99. Okay. And again, the worst is like 99.3, but two of these fidelities are, you know, super high. Okay, that looks really good. And that was a couple years ago. This was actually the first single electron silicon germanium quantum dot, this by the Delft group. And again, and it looks, I mean, I don't want to say it looks like shit, but poor gate fidelity, how's that? And again, much poorer. And it actually, you can trace to, these are the two valley states, right? Two different states at slightly different frequencies. The thing that matters is like the frequency you're driving at. And so when the two valleys have very slightly different resonant frequencies when you drive the qubit, and what you're looking at is just the interference between two different Rabi oscillations. And again, you can't make a quantum computer out of that. Okay, so it really matters, and you know, it's completely obvious that this is a problem you have to solve. Okay, so and again, what happened is when people did it, they just found that, you know, they weren't getting high yield of big enough valley splittings. And we just said, well, if you just, you know, eliminate the steps, then that should fix it, but it didn't fix it. So then we started thinking about, no, we're good. Yeah, we started thinking about ways to make it more deterministic. Okay. And so one was this thing which we called, I didn't come up with it, somebody did, called the wiggle well, and which is a short period modulation of germanium in the well. And it's sort of a bulk thing. Okay. And so there's some work on that. You'll see that it sort of well, you'll see. It didn't solve the problem. Okay. In the literature, I'm going to show you work from HRL, but this is like done by, you know, there's like a bunch of groups working on silicon germanium, and this has been done by several groups. But I'll show you HRL, which was really, I think, they did a pretty complete study quite early. Decreasing the well thickness does help. Okay. And what we're going to claim is actually when you decrease the quantum well thickness, actually that's true, it helps, but what it is it's adding germanium to the quantum well. Because when I'll show you the data, it's like very sort of random still. And then if you then say everything is because the wave function's looking at germanium and the different values see different amounts of germanium, it turns out it explains everything. Okay, and that's what we mean by universal. Okay, that basically if you put germanium in the well, there's a matrix element of that couples the two values, and the valley splitting is proportional to that matrix element. And no matter how you increase that matrix element, that's how you get, that determines the valley splitting. Okay, so I mean, but that's not as useful for experimentalists because it's not like there's a knob called matrix element that you can turn. But it turns out that theoretically it's quite simple. You're like, does this increase the relevant matrix element? And if it does, then it's a good thing to do. Okay, so I'm going to go through those three things in order and then I will stop. The wiggle well, okay, that's the thing where, so this is explaining like what the idea of the wiggle well is. The idea of the wiggle well is actually Bob Joint's idea. Okay, so I'm on the paper, but it's a cute idea, and I don't want to tell you that I thought of it because I did not. Okay, so basically these are the values in the extended zone scheme, you know, just because it turns out that here you want to couple the two valleys, and so you put a perturbation on at a certain wave vector. And what the most obvious wave vector is what is called K short here, all right? And I'll show you on the next slide, like if you could do that, that would definitely be the way to go. But the period is extremely short. It's only 3 angstroms, and so it's hard to grow. So in the original experiment, then what they did is they, you know, said, well, how else can we couple the valleys? And so you couple valleys, and this is in the first Brillouin zone, and this is in the second Brillouin zone. And this we call K long, okay, and that wave vector corresponds to a period of about 2 nanometers, which is sort of a much more reasonable thing to grow. Okay, so the experiments were all done at K long. Okay, so all right, so this is, I'll just walk you through. Okay, so again, this is the idea. You remember this is silicon-germanium wells, and then, you know, everything up until now was silicon. The well was made out of silicon. And, but now it's alternating silicon-germanium and silicon in the well. So it's silicon-germanium, but at 30% germanium outside, and then sort of a few percent germanium modulation inside, okay? And well, actually, yeah, so the average, well, I guess the average is sort of 10%, but still much less than on the outside, okay? This is a picture, this is a TEM of you know, a test sample. So it's not the thing that was used because you have to cut it, or you know, you have to cut it, slice it, and then you can't turn it into, you know, a device. But you know, this is the sister or brother device, you know, material. Okay. And then here is again, and also when you do this business, every time you see a device, it's not the actual device. Most people don't, you know, because there's a thing of like, when you image it, you worry that you're going to screw it up. And so usually you make 2 and you image 1 and then you measure the other. Okay. So that's the device. I mean, this one had a lot of dots, but you know, there was only 1 dot that they measured. Okay. And this is sort of just showing the, you know, single, you know, the characterization so you can see what it is. Okay, but now I got to get to this one. Okay, so here is 3-dimensional picture of the valley. So these little blobs are, again, where the conduction band minima are, you know, when you're a certain distance. And so that's, you know, this, and again, the KX and KY are not as low. The only thing that matters are the KZ. So the only thing that matters is what's happening vertically. And either you couple this one and that one. Oh, and I forgot one more thing. It's a repeated zone, right? So here's a Brillouin zone. Here's another Brillouin zone. It's you know, because the zones are repeating. And so either you couple this valley and that valley, or you couple like this valley and that valley. Okay. So, and this are equivalent to these 2. Okay. So this is K long. And then you get like, and again, this is a value splitting, and you can see that it, it helps. Okay. But, obviously better to be here. Okay. If you could do K short, if you could grow it, that's the way to go. And again, completely deterministically, but that, and so it is true that there's a grower at Wisconsin who's going to try to do it, but super challenging to grow. Okay. But the experiments were done at K long, where you say, okay, if we put in 20%, and so they did, at the maximum, then, you should get reliably 100 microvolts. Okay, and so what happened was that they then, this is not doing a whole bunch of different dots. What this is the one dot, and then you move the dot around. And there are two ways they moved the dot around. One was that they made the dot bigger and smaller. They just basically squeezed the voltage inward so that the dot changed its shape, okay? And when they did that, and they changed the shape by quite a lot, a factor of 2 in the orbital splitting, which is, a fairly hefty change in the dot. And they said, oh, look, there seems to be a deterministic, value splitting over 100 microvolts. This is great, right? But unfortunately, or fortunately, there's another way you can change the dot, and that is to like basically, increase this voltage and decrease that voltage, and it moves the dot position. And when they did that, they saw that the value splitting actually depended quite a lot on exactly where it was on the chip. And so that's, so this is like the first piece. And also this is bad, right? Because now it's not 100, right? So, this was good and everybody got all excited, and this is bad. And it's like the 13th ring of the bell, that if it sort of, goes down, it's not deterministic. Okay. So that's when we started thinking about disorder. Okay. And so Merritt is the one who did these calculations, who said, oh, okay, what's different between these two things? And one is that, you're sort of sampling a different region. In the one case, you're changing the dot, but in the other case, you're actually moving the dot. So something is depending on exactly where the dot is. And let's think about fluctuations in the germanium. Oh, okay. Oh, okay. Sorry. I changed the order. I wrote the talk. I forgot the order. Okay. So then that was thing one, which, was again, making a wiggle well, but the wiggle well wasn't deterministic. So the HRL group basically did a bunch of calculations. I'll show you their experiments in a minute, saying, oh, well, what you can do is you can take that original thing of, remember I was talking about, you have the, you have perfectly smooth interface, and then you just figure out how the wave function fits in, and then you calculate the difference in the energies of those states. They did that, but then what they did is they allowed the interface to smoothly vary with different widths. So 1 monolayer, 2 monolayers, 3 M is atomic, 3 monolayers thick. And then they varied the well width. Okay, but here there's no disorder. Like what they did, if it's like 30% germanium and 70% silicon, they had what's called the virtual crystal approximation, where it was a magic thing that had the parameters that were like 30% of the way from germanium and 70% of the way from silicon. Okay, so it was like it was a smooth dependence with no atomistic disorder in it. And if you do that, you can, calculate the value splitting. But they, I think, are the first people who published this thing about the thickness of the interface makes a really big difference. And so you can see, like, even at 3 monolayers, and just to cut to, well, I'm already cutting to the chase, but 3 is actually not more than the actual thickness of the interface. Okay, even here you see, oh, well, there's actually sort of a problem that if your interface is 3 monolayers wide, you never get to 100, no matter what your well width is. But if your thickness is like 2, then it definitely helps to make your well thinner. Okay, And so that was their thing of just thinner wells have higher valley splitting, okay? And finite interface thickness is important, okay? So those are two things that they published. What they then did is really quite a lot of growth and measurement. And okay, so here we have sharp interface and one atomic layer, here's 2 atomic layers, 3 atomic layers. And here you don't actually characterizing the thickness of the interface is, I'll show you the experiment, but it's not done generally. It's another one of these destructive techniques. So they're just fitting. They say, oh, here are our valley splittings, but we fit. We sometimes, well, with the 3, we do this, and then maybe the interface is changing its its width or something. Okay, but let's just look at this from the point of view of dumb people. Dumb people, you'd say, oh, look at all that variation. Okay, and so that's how we started interpreting this. This is like, well, this thing about exactly the thickness of the interface, but you say, well, look, there's a variability between thin and different well widths, and the variability is going up as the well is made thinner. Okay, and so so that's what we were thinking about. So there were 2 experiments. One we were involved with, but absolutely following up on Bob's idea of the wiggle well, where you say, oh, look, something's varying when we move around the chip, when we move the dot on the chip. But then the other one is that the variability of the valley splitting goes way up as the well width is thinner. And so what we then investigated, Merritt Loser did the calculations, was just this idea of, well, what's different with the thin versus the thick well is that the root n over n is smaller when you have fewer atoms, and it's bigger when you have fewer atoms. Okay, and when you're just reducing the number of atoms, and so sort of all these things that depend on square root of n effects are relatively speaking bigger when n is smaller. It's like if you flip a coin 10 times, your chances of getting 4 heads are really high, but if you flip a coin 10,000 times, your chances of getting 4,000 heads are very low. Okay, and so that the cause of this additional variability is not some complicated thing, but rather just square root of n. Okay, and so there's a theory which I will not go through in detail, but I can just say it's basically doing the same thing, but instead of making an atom that is 30% germanium and 70% silicon, every atom is either silicon or germanium. And then we calculated that. Okay, and it turns out that the fact that you get this, variability due to just, you pick which each atom is randomly out of some distribution, but it's either one or the other, and you just take that into account. Okay, so what this is here, so these are the experimental points reproduced from here. Okay, and these are exactly what you get. So it does depend, again, very sensitively on the thickness of the interface, but we're thinking about the spread. Okay, and you see that you get a much larger spread when you have a very thin well than when you have a thick well. Okay, so so what we claim is that you can understand these experiments. The disorder, the alloy disorder, is really important. Okay, so then we're doing this collaboration with the group in Delft, but then there's also a group in Ottawa. There's actually an extremely large number of authors on this paper, because it was like a bunch of experimental groups got together with the same samples and tried to do a really detailed characterization. And so again, to actually measure the thickness, they used atomic probe microscopy, where basically what you do is you sort of zap it, you zap your sample, and you see what comes out. You do it in a controlled way. You're like, well, this thing came out, it was germanium. This one came out, it was silicon. And then you reconstruct it to figure out, the statistics of what happens as a function of depth. Okay, and when you do that, it turns out that the interface is bigger than 3 monolayers. Probably I shouldn't have gone back, but I did point out to you that if it's 3 monolayers, then this deterministic contribution to the value splitting from the sharp interface is always small, okay, no matter what you do. And so it turns out that for all those years, you know, what we were thinking was determining the value splitting was not determining the value splitting, okay? And the other thing was that, you know, as I told you, like the effects of steps, and I spent, you know, really a good 10 years worrying about the effects of steps. Turns out if your interface is that wide, they have like no effect whatsoever, okay? And so actually this provides future employment for us because we can now redo the effects of Coulomb interactions and in double, you know, when you have a doubly occupied dot, which turns out to be really important. So we can redo everything, and therefore we can publish, yeah, we can talk about those idiots because, and then just not mention that we were those idiots. Anyway, but there you are. So basically the deterministic value splitting I told you about is irrelevant. The steps are irrelevant. And the only thing that matters are compositional fluctuations. That's what we said. Okay. And so, and basically then if you say, well, how do you determine what the value splitting is? You know, there are various things that people have proposed. I told you about the wiggle well. We talked about the narrow well. But then there are other things. Oh, germanium in the well, I told you. But then we also, there's some experiments on, you know, putting germanium in the well, like not uniformly. And basically what you can do is just do effective mass theory and, you know, take the envelope function that, you know, the envelope of that, you know, fast wiggle. And then more or less, and this is the quantum well potential. And you need the envelope function because if there's no wave function where the germanium is, it doesn't matter. So you need, is there germanium there? And then everything oscillates because, you know, you're near the Valley minimum and this is the, you know, this is basically the oscillations in the wave function because of the Valley. And it's 2k0. It's like, you know, what couples the two valleys. And it turns out the only thing that really matters is that, you know, really small wave vector, because you saw like the value splitting when you just calculated it directly was so much bigger. And the k long, you know, sort of, you know, is just a very small correction. Anyway, if you do that, there are all these different ways of trying to get big value splitting. And it's all just like, that's the, it's just the size of that matrix element determines everything. Okay, and so then you do this and it says that, again, our goal is to get the value splitting to be high. And one thing you can do that seems pretty simple is just put a little bit of germanium in the well. Don't worry about making it have a particular wave vector. And if you do that, the value splitting will go up, okay? And again, this is a matter of, you know, real interest to the community. And so we published our paper sort of this, we published a paper like the one with like details of everything was like mid last year. And already at the March meeting this year, Intel reported like, you know, a bunch of experiments because again, they feel, and they also hired one of our students because they really feel this is like directly relevant to their plans. Okay. And so again, the scale of this, I should say they published a paper in Nature like really recently, which was just like the scale of what they can measure efficiently is just incredible. So, okay. So, what to say? So what I was going to say here is that I've been talking about the value splitting here. Okay. And here you can see I did not make up that everybody thinks that, or, you know, it is generally accepted that, you know, it needs to be more than 100 microvolts because this is in millivolts, so 0.1 EV. This is brand X, which is, again, just what they were doing, silicon well, silicon-germanium, silicon-germanium, like in between. Here's the well, germanium concentration. Okay, and here are all the things they tried, again, in just a few months, as far as we can tell. So here's the thin barrier. What's thin barrier? Thin barrier, I think was like they had it and then they had a, you know, tried to make the silicon germanium thin. I don't know who thought this was a good idea, but it didn't really help. So I'm not going to worry about why they thought it was a good idea. The 0% is really bad. Okay, then this one is putting silicon-28 in the well. And this we actually think is it turns out their silicon-28 is contaminated with something, so we think it was a similar, there was probably a similar disorder effect, but again, they don't want it to be contaminated, so let's not worry about that one. But then thin well, you heard about thin well. Again, that's making the quantum well thinner. And again, we think that it does improve from 22.5 to 56, but we think that's because the reason we told you is like if you have a thin well and you have finite width, I'm good. You have finite width barriers, you just get more germanium in the well anyway. Okay, so we think that thin well is a subset of germanium in the well, and this is us, and you can see it goes up to 88.2. That's significant. 83.3 is germanium in the well, and 88.2 is germanium in the well. And so it was the best of the things they tried, and this is us. Okay, so we got us inset in their figure because it was the most successful thing. Okay, and if you do that, then okay, but the problem is, okay, first of all, as I said, you don't want 88.2, you want 99.99999. Okay, and so we think we have ideas on making it a little better, but now you're really stuck with manufacturability, because once you're doing things on an industrial fab, you say, well, why don't you change this, right, in your design? And in a university fab, they can do it. In an industrial fab, they're much more constrained. But the point is, we're the best of the options at the moment. Now this though is the bigger problem, and I haven't talked to you about this. It's something that again we're actively working on. So it turns out like it's important to have the valley split being big enough, but for various reasons, it's also important to have what's called the singlet triplet splitting be big enough. And that is if you put in a second electron, okay, if they're both in the ground state and form a singlet, and then that's a state with an energy. But if you have two, if you have a low-lying valley, then what can happen is that you can have the same spin state, all right? And if you have the same spin state, then the Coulomb interaction prefers the spins to be parallel. If you've heard of Hund's rule, it's same reason is because of Hund's rule, that that basically because the spin states are the same, they sort of naturally don't overlap, so the Coulomb interaction is less effective if it has an orbital state to go to. Okay, and it turns out that for reasons I'm not going to tell you, but exist, you really want both the valley splitting and the singlet triplet splitting to be more than 100 microvolts. And we still are, this one is the best of the options, but they're all completely unacceptable. Okay. And we've done like enormous amounts of work on singlet triplet splittings in this with the flat interface and with steps. But again, all of those calculations have to be redone. And what we're really thinking hard about now are strategies to, get this number. I mean, this number, we think we have, a lot of ideas that we can try, but getting the singlet triplet splitting to be large is going to be, that's the biggest problem at the moment. Okay. I shouldn't have said all that. That makes it sound like we have a problem we don't know how to solve, but we do. So there you go. But they have other collaborators, and I mean, they're talking to us because they care, and I can't tell you exactly what's going on at the moment because I signed an NDA, but what I showed you was public. So that's okay. So the fact that they admitted they had a problem was incredible in some ways. Okay, so let me summarize. I hope I sort of convinced you that valley splitting, though it sounds really dull and arcane, actually is the leading physics problem in the scale up of silicon-germanium at the moment. Okay, and I think there's that and there's crosstalk. There are two things And getting this solved is important because you just don't want to have to worry about it. The thing which I think was, I think is quite convincing. Oh, and that was the thing I said, right? They measured the value splitting by putting in germanium in the well, and it went up. I forgot to mention that, we predicted that they should try it, and it actually did it. Okay, so I think doing that is clear that that's a useful, useful contribution of theory, was just dumping germanium in the well does on average increase the value splitting. And basically we're looking at doing other things. The wiggle well still is a good idea. But again, for years we focused on the interface and the steps, but it turns out they're totally irrelevant. And so we think that by looking at the physics that actually is dominating the value splitting, we may be able to stop working on this problem. Okay, so again, here are the collaborators. So I talked to you about everybody, didn't I? Yeah, so again, Mark and I were, the theory, and Merritt, Merritt did most of the calculations. Ekmel is the guy. Oh, he's at Intel now. I forgot to change that. And so he's the guy they hired because they realized they really cared about this problem. But then a lot of other people contributed really critical parts to the work. Oh, and that's it. That was the last slide. Thanks.
Sorry, I didn't get this part. Where the electrons of the triplet are going to lie in the band structure picture?
Oh, well, okay. So think about the atomic, think about the hydrogen atom. Okay. There's like the S state. Okay. And then there's like the P state. And if you want to make a triplet, you put the spin up, and then you don't have spin to work with, right? You have an electron in the S state, and then there's no other place to put it. You have to put it in the P state. Okay. And but then there is like okay, so, and that costs energy, and that's a single particle energy. That's the analog of the value splitting. Okay. But if you make a singlet, you can put an electron in the S state, and you can put a second electron in the S state. Okay. And so what happens is that the single particle energy, which is the analog of the value splitting, is like high for the P state. Then you turn on, and so the singlet is the ground state, but that's because that single particle energy is big. Because if you then think about Coulomb interactions, these guys to 0th order overlap, right? It's the same state. So they got to get out of it, and they don't have to get out of each other's way because of statistics, but the Coulomb energy doesn't like that. So they have to deform. And so it turns out that when you turn on Coulomb interactions, the ground state, goes up in energy just because the electrons are repelling and they're stuck near each other. Okay. Whereas when you have two orthogonal states, the Coulomb is not as effective just because the states are orthogonal. I mean, there's still Coulomb, but it's smaller. Okay. So relatively speaking, the two particle energy is lowered relative to the single particle energy. But again, in hydrogen, that single particle energy is big enough that, there's still a pretty big singlet triplet splitting. Okay. And here the problem is that single particle energy, which is the value splitting, is if that energy is too low, then the Coulomb interactions sort of drive the singlet triplet splitting to really low values. And so I think it's okay because it's us, it's not Intel that, is doing this. What we're thinking about is, you can just make the dot smaller, and that increases, it sort of makes the wave function more rigid if you think about it, because, it's sort of like the electrons are trying to get away from each other. Like in the one case, they're sort of naturally orthogonal. In the other case, they have to get away from each other. So making the dot smaller actually makes it more likely to get a large singlet triplet splitting, because it makes it harder to deform the wave function to accommodate the Coulomb interaction. Yeah, and so basically we're futzing with confinement, and one of the things that we're looking at is also vertically you know, whether it matters vertically, but at the moment, we're looking in the plane, assuming, you know, assuming that everything is happening in the plane. But hopefully that was clear. And that's why I said Hund's rule, right? You know, with Hund's rule, like, you know, elements, the electrons tend to align because again, if the spins are the same.
It's the competition exchange interaction in the quantum.
Yeah. So it's the same physics, but in this, you know, so you learned it in school. Okay, yeah.
But one of you had that slide with was 2022 paper in Princeton with the high fidelity and the
Oh, yeah.
and on the right.
Right, that was a 2014, yeah.
So structurally, what's the difference between the two systems there?
Well, actually, there were two things. There was the one I told you was that, you know, that was the very first one. Okay. The one in 2014 was the first single spin qubit. And it just happened to had you know, they got all set up, had a really low value splitting. And it was low enough that you could never actually occupy a single valley. Okay, so they were just sort of screwed from the word go because, you know, they had no way of initializing into one valley. So you always saw two valleys. Okay. The other thing about the Princeton paper, though, is that that one is what's called a flopping mode qubit. So the one in Delft, you know, you had a quantum dot and you're like moving it around. Okay, but inside the quantum dot. And you get a certain size, you know, for a given drive, you get a certain amount of motion. But one of the clever things that the Princeton group, well, it's Jason Petta, now he's at UCLA, but okay. One of the clever things he did was they did it where they put it in a double dot. And then when you drive, you actually like are moving it between dots. So for a given size of, you know, electrical drive, you're getting a bigger magnetic, because you're doing this with essentially an AC magnetic field. You have a field gradient, and the farther the drive moves the electron, the bigger the magnetic drive is. Okay, so part of it was that they had a reasonable value splitting, and part of it was they had a way to get to higher drive. Okay, and those are the main improvements. Oh, and that was an isotopically enriched sample. So that original thing also had the issue of it had silicon-29. It had a, you know, natural abundance of silicon-29. So it's going to look shittier no matter what, but it looked even more shittier for these other reasons. You see what I mean? But again, the big problem was the valleys. You could, you know, because it was like 20% in the valley you didn't want, and so that dominated the infidelity, and so that's why I felt it was like fine to tell you that. Yeah.
But because can you remind us why the conduction band minimum is not at the Gruen zone boundary? And it's just because I know it's
Sorry. Why is
why are
silicon?
we 85% away from the Gruen zone? Just because of the Gruen zone 3D shape of the Gruen zone.
I'll tell you, I used to know better. I'm trying to remember. I think it's this thing. It's like there's SP and D orbitals, and essentially what's happening is that it's like there's a plus and a minus and a minus and a plus, and so it's sort of like, and there's like an almost every other atom thing happening. I think it's because of the, you know, of the zinc blend. Yeah, I mean, you know, again, I know who I can sick you on in terms of he'll give you like a story of why it is.
Get an easy explanation.
I do not. I'm just like, it's band structure. You tell me, I believe you. You know, I mean, so, but I know someone I could sick you on to who probably would have a good way of explaining, but I just took it as given.
Just not intuitive.
Well, I mean, okay, so let me go back to like this, actually the very first paper I wrote on silicon-germanium. So you say, well, how do you get that? Okay. And this absolute simplest model that gives you a band structure that is sort of like this is what you can have is nearest neighbor and next nearest neighbor hopping elements. Okay. And again, and then if you just sort of futz around with the ratios, you then can, and our first papers were like this, you just futz around with that, and then you can futz around with the size of the matrix of these two hopping things, and you can fit to the location and the effective mass at the minimum. Okay, so it's absolutely the simplest model of valley splitting you could write down. So that's how I got into it. It was like, because people in the business are like, well, we're going to do something realistic. And I just came from stat mech, where you just make up, completely stupid, simple models. What's the absolute simplest thing you can write down? So I wrote it down, and actually it's not perfect, but it's really very useful. And again, and again, the guy I would stick you on is a guy named Tim Boykin, who's, really a specialist at, the density functional. But the point is, it's sort of like, it's, how to say it. If you look at silicon, I don't think I have a silicon band structure here. But it's sort of like two interleaved, it's a diamond lattice. Okay. And there's sort of like, if you look at a guy, there's like this guy here and that guy there, they're sort of like offset. Okay. And you say, oh, well, then this is the close one. This is the nearest neighbor. This one's the second neighbor. Okay. And I think there's a sign that has to be the right sign in order to work. But again, just the way the atomic orbitals are, it works out to have that sign. Okay. So Tim actually wrote, I think I can refer you to a paper where Tim actually pseudo-derived the simple model from silicon band structure. And that's my recollection of what was going on. Again, it was like, there's a guy over here, here's an atom, there's a guy here, and then there's a guy there. The distance is not that different. And again, and it has enough symmetry that you can think of just taking slices.
What is it?
Okay.
1D, that one?
No, that is a 1D model I'm talking about. But again, you need nearest neighbor and second nearest neighbor. If you only have nearest neighbor, you never get this. Okay. So in that sense, in 1D, it doesn't work. But if you have 1D, but with, where, no, can't do it. Can't do it. Okay. Yeah. So you have like atom, atom, atom. And if you only couple nearest neighbors, no. But if you have atom, 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 and this guy's coupled to its nearest neighbor and second nearest neighbor, then it's a totally 1D model, but with a long range interaction. You can do it all. Okay. Which is very handy, because 1D is much simpler than anything else you can do. So in like 2004, we wrote I can refer you to this paper. I mean, it's, again, completely wrong in many respects, just because, yeah, but qualitatively, like he wrote like a long thing about like how you can sort of pseudo derive it using, atomic orbital theory. But that's that was my recollection, was it was just that, oh, here are two atoms are pretty close. And, and so this one, and again, it's like, here's a more or less cubic thing. And then this next layer over is like also cubic, but offset. Okay. And then it goes back, and you see what I mean? That's sort of the way a diamond lattice looks like, So that's my understanding. Okay. But it's like, well known, of course, that silicon has this property. I mean, it's not in debate. But yeah. Okay.
No more questions? Thank you very much, Sue.